Hello, welcome to an ACM webinar. This evening, we have a presentation by a senior from a local high school. And the topic is measuring and improving engagement in online learning. A little bit about our ACM chapter. We were founded in 1957, one of the oldest organizations for software professionals. We promote knowledge of modern computing, and we create a community, a support environment for these professionals. We ask that if you're able to please support us by becoming a member. It's $20 a year, and you can go to our website, which is sfbayacm.org. Typically, we have 2 technical meetings a month, one in the area of general computing and the other in the area of data science or big data. In addition, for those who have job announcements, please feel free to put into the chat any information about a posting that you might have that you would like to see advertised. In addition, we also have relationships with other professional organizations such as the IEEE Society and Valley ML. For the presentation, we ask that Q&A be, if you have questions, please in chat raise your hand, and a moderator will either respond to your question or may defer it till the end of the talk, depending on how the speaker wishes to handle those questions. Okay, and with that, I will stop sharing and let the speaker introduce herself. Thank you very much.
Hi, I'm Ana Siganti. I'm currently a senior. I'm a rising senior at Monte Vista High School. In terms of computer science experience, I was a research intern at Stanford University for a year, and I'm currently an intern at Alation Incorporated. And I'm really excited to be here.
Fantastic. Okay, Manasi, would you like to share your presentation now?
Okay, cool. Yeah. My name is Manasi, and my project is focused on improving student engagement in online learning using machine learning models. Before I start, I want to thank the ACM for giving me this opportunity, as well as the Synopsys Science Fair, and my mentors, Colin Anderson, Dan Fu, and Chris Ray. So the goal of this project is to help students engage more with online learning. I created a program that allows students who are uncomfortable turning on their video to convey relevant emotions and engage with the lesson by detecting specific actions such as smiling or raising a hand and conveying them through pictures. It also helps teachers feel more comfortable and less like they're talking at a wall of icons. Originally, the application focused a lot more on measuring and reporting the data to teachers so they could identify gaps in their teaching. However, I realized there were ethical issues with monitoring engagement and sending it to the teacher, even if it was anonymously. So I shifted the focus of my project to have more use for students. Now the main goal of the project is to help students who can't turn their cameras on for whatever reason, as well as teachers with those students. Engagement data is still compiled, but it's for students to view for themselves, not for teachers. This application is more tailored for students, allowing them to customize their own avatar and giving students the power over their information. So today I'm going to go over first the problem that inspired me to create this app, then the existing technology, the approach that I took, my initial results, and my conclusions and improvements that I'd like to make in the future. My entire junior year and part of my sophomore year was online, and I noticed a lot of students spent their class with their cameras turned off, sometimes myself included. When I talked to my teachers about it, they said that it was disheartening to be teaching a wall of icons. One of them even said that they feel like a comedian bombing every night. There are reactions in Zoom, but they're rarely used and can never really replicate real emotional reactions. It's awkward and artificial to convey engagement and emotions through the click of a button. Some teachers mandate that all students turn on their cameras. However, I was sometimes uncomfortable when I had to turn my camera on, so I can understand why students may not want to do so. Teachers would also have to constantly enforce that rule and examine all their students' videos to manually gauge and monitor engagement or lack thereof. So I started this project, aiming to create technology that helps teachers easily improve engagement without forcing cameras to be on. Afterward, it also gives students a report of their own engagement so they can identify where they need to improve in terms of staying focused. Ideally, students would then anonymously share their reports with the teacher who can know where they need to make their teaching more engaging. In essence, it's a more natural and genuine way to communicate real-time reactions without edging into invasiveness. There are multiple methods for measuring engagement, so I had to evaluate each one to figure out what would work best. From simplest to most intensive, I researched surveying students, using emotion recognition APIs, building on facial recognition libraries, and training a model from scratch. A survey-centric approach would involve teachers periodically surveying students to gauge engagement, either during or after every class. However, there are multiple issues with this. First, the logistics of distributing a survey can be tedious. Even if it can be programmatically pushed to students regularly, it's unlikely that students will be honest or thoughtful when answering the survey, or even have been monitoring their own engagement levels enough to be self-aware and accurately analyze their own engagement during a survey. Additionally, it's likely that many students will not even take the surveys regularly. And on top of that, teachers have to analyze them and draw their conclusions by looking at each individual survey and aggregating the results that they get in their head by themselves. On the opposite end of the difficulty spectrum is a custom machine learning model. It would involve classifying students' expressions into categories that involve with student engagement, such as engaged, confused, or bored. However, this requires a large amount of training data, which has to be manually labeled and is very hard to acquire. I did try to train a custom model, but I found it wasn't very accurate because I didn't have enough training data. So I decided to move on from this approach. Another approach is emotion recognition APIs. Existing expression detection APIs focus on basic emotions like happiness and fear, so they're not really useful for online classes. So I'd have to extrapolate engagement from the basic emotion results. However, along with the custom machine learning model, they could be useful avenues on top of my main method to help improve accuracy and specificity of detection. So I settled on a hybrid machine learning and rules-based classifier approach. I found the libraries OpenCV and dlib in Python, which are face and facial landmark detection libraries. And I used the dlib 68-point landmark math to find markers for facial landmarks and from there detect actions. The app on the student's computer would detect engagement, detect actions, and then extrapolate engagement, and then display those actions in a video call. The teacher would then be able to see this teacher and all the other students in the video call would be able to see this displayed, their displayed actions and be able to catalog more easily how their students are faring. Then afterwards, students would get their engagement reports and could optionally send it to a teacher who would be able to get an average engagement report over the class and figure out where they need to improve their teaching. First, like I said, the app detects actions by analyzing changes in facial expression, and then it extrapolates engagement. Each detected action usually implies a state of engagement. Actions like smiles usually imply engagement with the lecture, but squinting, while it does imply attentiveness, also implies confusion. Other similar associations are used to derive engagement from the detected changes in facial expression. Obviously, these are generalizations and not always accurate. And the current solution for that is to have a lot of factors and detections that go into the overall engagement score. But in the future, like I mentioned earlier, integrating the previously mentioned emotion detection APIs or a custom machine learning model could be helpful, as well as finding other methods to make the emotion detection more accurate and specific. I experimented a lot with how to detect actions, starting with a simple rule-based classifier. Like I mentioned, I tried training a machine learning model, but it wasn't accurate enough. So I returned to the classifier with some key changes. In order to make it more accurate, I included a calibration step, where the program detects the user's baseline facial expression and uses it to find thresholds for detecting actions. It can then compare the distance between facial landmarks to the baseline to determine if a change in facial expression is occurring. For example, to detect a smile, we compare the width and the height of the user's mouth to the baseline. And then the program also uses the height to make sure that an increase in width is not due to the person moving closer or farther from the camera. For example, in this case, while the width increases by a significant amount, the height stays at around roughly 20 pixels, showing that the person is more likely to be smiling than moving closer or farther from the camera. And hence that's how it detects a smile. To detect, for example, another example is to detect eye widening, where the program calculates the aspect ratio of the eye, which is the ratio of height to width. To find the height of the eye, it averages the two vertical distances between the existing facial landmarks on the eye. And then the eye aspect ratio is compared to the baseline eye aspect ratio. If it's increased by a significant amount, it is determined that the person's eyes are wider than usual. If it's decreasing by a significant amount, it's likely that the person is squinting. So the squinting method to detect squinting is virtually the same as the method to detect eye widening. To detect whether the user is closer or farther from their camera, we compare the width and height of the user's face to the baseline using the face aspect ratio, which is the ratio of the height of the face to the width of the face, to make sure that an increase in width or height is not because the person is moving their face in different directions, like sideways or up and down. If the aspect ratio stays the same, then that means that the increase or decrease in width and height is likely due to the person moving closer or farther from the camera. Are there any questions on how this detection occurs?
At some point, I wanted to ask about the technology behind this. I mean, it seems to me this is really a very good thing that could be very useful, as you pointed out, to teachers, but also in general in other situations. And I would think that a company like Zoom, for example, would be very interested in hearing more about this. Leanna, were you saying something?
Yeah, Tom have a question here. Say, if a student for a moment turns to look to the side, does that interfere?
No, it doesn't. The face is still detected and the landmarks are still quite clear. But obviously, because it's to the side, the face is not head on. So the height and width would be, the width would be slightly smaller than if the face was direct. So that's actually a method used to detect if the user is turning, where if the width is significantly smaller and the height remains the same, then it's likely that the person is turning. But it's also how the program makes sure that, for example, detecting if the person is closer or farther is not because of the them turning to the side. If that makes sense.
I think you can continue on, Manasi. It doesn't look like there are any more questions at the moment.
Okay, cool. Yeah. So moving on to how I displayed the actions. I originally planned to create a virtual webcam, which is basically another video source, as you can see in option 2, using Apple's Core Media IO library and making a plugin for that would create another video source as an option. And but because of the security and permissions of a lot of video call apps, I wasn't able to finish to make it work, but I'm still working on trying to get it to work. But because of that, I switched to using the Zoom API to change the user's profile picture and reflect detected actions during a meeting. Basically, the user uploads the images they choose as reactions for each action, and then the program will call the Zoom API's post method and change the profile picture in real time. And it will, as a reaction to the action that is being detected. This is an example where some actions that are detected and mapped to an uploaded picture, where the user can choose the pictures that they uploaded. In this case, I'm using an avatar creator called PyCrew to create corresponding avatars for each of the detected actions. And but the user can choose whatever they wish to reflect the actions that are detected. Each action has a corresponding picture that is, or reaction that is displayed when that action is detected. Then to compute the score and then report it, each detected action adds or detracts from an overall engagement score and is weighted with higher or lower magnitudes depending on how overt the action is. Behaviors associated with engagement are weighted positively, and behaviors associated with a lack of engagement are weighted negatively. Additionally, the program returns a breakdown of how much time was spent on each of the actions that are being detected as a percentage of the overall time measured. In this, and this is also an example, here's also an example of the engagement graph, where the horizontal axis measures time from, in this case, from 0 to 70 seconds, and the vertical axis measures the engagement score from -1 to 1. In this case, it appears that the engagement started to decrease rapidly and then started to increase a little bit more gradually in this case. So to download the app, the user will have to install the package from pip and retrieve as well a Zoom API token associated with their Zoom account. And then they can replace the images in the downloaded folder with their own images. And then they pass their Zoom account, the meeting ID, and their personalized API token as arguments when they run the program. As you can see in this image, in this demo, my webcam is on the left and the video call with my displayed avatar is on the right. And when I smile, you can see that the avatar will follow and also smile. The corresponding pictures are slightly different than in the example earlier. Now my eyes are, I'm raising my eyebrows and widening my eyes, and you can see that the avatar followed. And now I'm squinting and the avatar does the same. And then when I smile again, the avatar will also follow. There is a slight lag in terms of when the avatar copies the user's actions. Then once I quit the program, in my documents, I can find 2 files titled with the date. One will be the CSV file with the breakdown of actions, as I showed in the previous slide, and is right here. And one is the image of the engagement graph, as can be seen here. So I tested this program on 17 people and then asked them questions after they tried out the program. The first question I asked was, how accurate was the avatar when it reacted to matched actions? And my responses ranged from, the possible responses ranged from 1 out of 5, which was not at all accurate, and 5 out of 5, which was very accurate. As you can see, most people responded with the 4 out of 5, and the average response was 3.72 out of 5. I think that some of the decrease in accuracy would have been due to the lag that I mentioned earlier, but I think overall the avatar was reasonably accurate. Because of that lag that I was worried about, I also asked that question in my survey, and I received answers. The options were from 0 to 10 seconds, and the answers range from 1 second to 6 seconds with an average of around 3 seconds, which is not ideal. I would like to improve the speed of the response, but I think 3 seconds is still short enough that one can associate the action with the following reaction. But that's one thing that I'd like to improve, perhaps by finding a more quick display method, or by making the processing more efficient so that it takes less time to return a result. And I would also like to improve my assessment of engagement further with the engagement score computation by adding more actions, which would be more dimensions to compute engagement, as well as trying the machine learning model, again with more training data, and using emotion detection APIs. This way I can improve accuracy and specificity for each person's detection, and then as well as their engagement computation, so that people with faces different from the generalization, such as people with glasses or whose expressions are more minute or less immediately mappable to an emotion, can still receive accurate results. I would also like to test the program with a less subjective measure of accuracy. For example, a way for users to give live feedback while their actions and the display is still fresh in their memory. Another change, another aspect that I would like to change is, or improve further, is the reporting, and adding average reports over several classes in a course for each student, so they can see if there are any patterns with their engagement, as well as for teachers, optionally, if the student consents, to highlight sections of the lecture that are more distracting or confusing for multiple students. In conclusion, I think that while there is room for improvement, the goal of creating an intermediate option between either turning one's video on or turning it off is achievable, as shown by this project. And I think that students don't have to sacrifice their comfort for the teachers, and teachers don't have to sacrifice their comfort for students. And although many students are returning to in-person learning this coming fall, I think this application still has many applications for example, flipped learning, which is gaining traction in a lot of schools, which is where students will watch videos to learn the content at home and then do problems in class with the teacher's help. So teachers can assess whether students are accurately understanding the knowledge that they are learning at home while watching videos. And as well as once privacy issues are explored and dealt with, things such as ad testing or initial screening for other media, and as well as just for fun and regular video calls among friends. Thank you for listening. The link to my GitHub code is on the screen, and let me know if you have any questions.
So Tom Moran has another question. Do some expressions take longer to recognize? In other words, a smile in response to a joke versus squinting responding to a confusing statement?
In terms of expression detection, mostly once the facial landmarks are detected, the individual processes for each action is roughly the same, because it's pretty streamlined, because it's usually just a very quick process once you have the facial landmarks to find the ones that are relevant to the action and detect how they have changed from the original. I think there might be some more involved detections might take more time, but I don't think so. I doubt it, because most of the time is the time taken for each detection is very short. It should be,
Yeah, it sounds like at this point, the time is mostly spent in displaying the graphic there, the icon. Would that be fair to say?
Yeah, I think it's likely that a lot of the time is going to calling the API and posting the picture, which is why I'm currently exploring the other virtual webcam option.
Leanna has asked a question. What language did you use to program this project? What libraries?
I used Python, and for face and facial detection, I used the libraries OpenCV and dlib. For displaying the engagement graph, I used matplotlib, and those were the main libraries.
Okay. And did you do the training? You trained this machine learning model, is that right?
I did train a machine learning model, but I had to, I eventually switched my detection method because the machine learning model was actually less accurate than the rule-based classifier because I didn't have enough training data.
Ah, yes. What, let's see, was it, so all this, the Python code with the library and the rule-based system is all running locally on the individual's machine. Is that right?
Yes, that's correct. I mean, another goal would be to have a cloud service where students and teachers can sign in and view their reports. But yeah, that's not something that I've put into production yet.
Did you try out this application out with any teachers? Have them take a look at someone on the other end doing, using this?
Yes, my mentor, Mr. Anderson, tried it. I wasn't able to get most of the class to use it because of there's still some support that's necessary in terms of downloading and using the package, but my teacher looked at it and tried it with, as well as I tried it with other people in a joint video call, people who I surveyed.
Yeah, I mean, it looks to me like a nice proof of concept showing that, you can get some traction with this, some ability that the idea works, which is a good starting point.
Yeah, I'm hoping to eventually get it into a easy to use app that's for people who are not as familiar with Python and command line.
Are you, do you have any plans, or have you talked with your advisors on any plans about going forward with this?
Not as of yet because of summer, but hoping to talk more about it once school starts again.
Okay, and how many students participated in your test? And
17 students
that's
tested the application. Yeah, sorry for interrupting.
no problem. And do the students see each other's avatar?
Yeah, they can see it's shown as the profile picture, basically. So everyone in a video call can see everyone else's current avatar.
Right, just like on this call where people can see the either the avatar or the name or whatever the person chose to show.
Yeah, exactly.
Okay, so we could have used this kind of thing on this call, perhaps, I mean, that would have been perhaps a bigger test than you were able to do so far. But I mean, it would have been theoretically possible to do that.
I think, yeah, it's actually, it would be quite possible to use it once you download the package. It's relatively straightforward to use. And yeah.
That would be pretty cool. Does anyone else have any other questions? You can use chat as you see at the bottom of the screen, or you can go over to reactions and raise a hand if you like. Okay, so we have Dan, you raised a hand, Dan Fu. Can you unmute yourself? And
yeah, I'll plant a question that maybe Manasi knows the answer to. Do you have any plans to build a tool like this for any other platforms? Maybe certain ones that you have particular connections to?
Yes, like I think the virtual webcam would work for any platform, as well as this, the Zoom API approach can be used as well for other platforms. And I think there should be other platforms that have similar API methods. And like I said, the virtual webcam would work for any video call or video application that uses webcams. I think there's possibly other methods to display that would work as well once I explore more varied video call applications, because as my online school was occurring on Zoom, I was working more on focusing on Zoom as the immediate use for this application.
Someone on YouTube, we were getting a question relayed by Tom. Someone asked, I missed how the input is captured. Is it from the webcam? Is it a video or an image?
The video is captured from the webcam. It gets, using the OpenCV library, it gets the webcam and processes the frame every second, because if it were every single frame, it would be a little bit, it would slow down the processing a lot, so it processes every second, the frame every second, and analyzes that frame by detecting facial landmarks and then actions from there, which is also why the engagement score and graph is plotted by the second.
And let's see, Leanna asked, the application, is the application installed on each participant's computer?
Yes, that currently that's how the app works. Like I said earlier, the cloud service or would be a potential goal, but currently the application is downloaded on each individual computer, and the person will run it and when their video call starts, and then end it when the video call ends.
How long did it take you to develop this? In other words, I mean, in terms of calendar time, not in terms of hours worked, but when did you start developing this?
I think I first thought of the idea in maybe, I guess, like a year and a half ago. so this project took multiple forms. First, I was like working with different libraries, and then exploring, and I did a lot of research in terms of how to get each step completed. And like I said earlier, I switched the focus from reporting and monitoring engagement to detecting actions and displaying them so students could get more use out of it. And so I started this version of this application in September, last September, around the time that I submitted, around a couple months before I submitted it for the Synopsys Science Fair.
Okay, and so this was a few months, less than a year of time that calendar time that this took. So that's pretty good. Had you had any experience with machine learning or this type of thing, image recognition beforehand?
No, actually, I started learning this a year and a half ago. Like I said, when I started working on the earlier versions of this project, and that's when I started learning like image recognition and these libraries that were necessary, as well as the how to train these models. Yeah.
Okay. Joshua Klipstein asks, do you know what language you can use to make your app for a mobile platform?
I have not looked into a mobile version yet, but that's definitely something that is a really good idea to explore. I was working on, when I was saying the virtual webcam is in Objective-C as an Xcode plugin. So that is something that could likely be repurposed for a mobile version.
Mm-hmm. And Raj Durai, I'm sorry, I'm mangling the name, but Raj asks, does this work only on desktop or does it work on other mobile devices? I think you've kind of answered that, but go ahead.
Yeah, the current library that you can install like online with pip is only for desktop devices because it requires installing with the pip package manager and some command line. And it's a Python package currently. Yeah, but like I said, a mobile version is something that I would love to explore.
Okay, and this does require having the webcam on the person's Zoom call, right? So if they turned their webcam off, what would happen?
On a Zoom call, they turn their webcam off, so nobody would see the webcam. The program accesses the webcam through OpenCV, which is separate from the Zoom call, and it doesn't show the webcam to anybody. It just uses the data from the camera source.
Oh, okay. Leanna, do you have a question?
Yes, I do have a question. She was just saying that he used the data underneath the webcam. Is that the data collected during the exercise or during the meeting, or it is from a previous meetings?
Once the program starts running, it starts collecting the webcam data using OpenCV. So it gets each frame from the webcam and analyzes it. And then from there, uses the Zoom API to post to Zoom.
I see. I see. So you do have to look through a lot of those data and to screen out the ones you cannot use. For example, a person turn around or go off and have a cup of coffee. And for those kind of cases, do you have a thought on how to capture and then put into the data or pick that out from the data?
It detects, like, if the person would turn around or leave the field of the camera, then it would the program would be able to tell that there is no face detected, and then it can take appropriate actions from there and change the engagement score accordingly, as well as post the correct reaction if the person is not in camera.
So is this data capture module, is it on the GitHub, or where? How much did you use it?
I used I used OpenCV, which is a Python library, and it basically has a function where it can create a video stream, or it can get the source from the video stream that is the camera and turn on and get the webcam images frame by frame.
Okay.
That's a capability of the package.
Now, do you, if you did that, you have that 17 students to cooperate with your testing. Did you have the 17 set of data you can use?
Yes, I would have to ask each of the people, each person to send their data from their local machine to me, because as of yet, it's the program runs entirely locally, so it doesn't have the capability to automatically send data.
Okay, well, that's very interesting. So it has become a private data that you have to ask them to contribute back to you for your, I would say, research. Is that correct?
Yeah, that's correct.
Okay, well, that's good to know. Okay, well, does anybody else have any other questions? Okay, do you have any plan to further working on this application?
Yes, currently I'm working on the Xcode plugin, which would actually improve a lot of the issues in terms of lag and usability, hopefully in one fell swoop. But yeah, that's what I'm working on currently, and it uses a virtual camera, so it creates an entirely new video source that users can choose in their video call applications. That's the current thing that I'm working on, and then after that, I'm thinking about improving the accuracy of detection.
Okay. All right. Well, that's good to hear you. And hopefully, are you going to continue work on this project and to attend next year's synopsis competition?
I actually haven't thought about entering synopsis, the improved product project, but maybe yeah, it's actually a good idea. Yeah,
okay.
Thank you.
All right. Yep. So I think if you got all the data collected from all your 17 students to work with you, then you got a good start to actually to get into deeper onto this data science project. Yep.
Yeah, that's a,
Okay.
yeah.
I think, does anybody else have questions? I think I got everything out here. Okay, well, thank you very much. Well, hopefully to see you later in the next year too, huh?
Yeah, that would be really cool.
Okay. Well, thanks. Well, next time, let's start contact earlier, not the last minute type of thing. Well, thank you.
Thank you, Manasi, and congratulations.
Thank you. This is really cool. Thank you for giving me the opportunity.